This is how I made the airfoil, or the curve for the blade. What I did was I just took the circle. It's 110 millimeters in diameter. That's the diameter of my turbine. And then I drew a line here along the side. That's 0.264 times the diameter. And then where it intersected with the circle, I just drew straight across, and there's one center point. And up on here, I drew straight across, there's a second center point. And so you can take an arc going from the center point from here to where it meets here, and then draw an arc from this center point until it reaches the side of the turbine. So that's pretty much it. It's just this one dimension here. I have 0.264 times the diameter just because I wanted to have like 30% of a gap here. If you want to vary that, that's fine. You could just do a quarter of the diameter if you wanted to. That'd make it nice and easy. So, but anyway, that's how I came up with that curve. Okay, what I plan to do with this small wind turbine is to drive this little boost circuit. I got this off eBay for less than $2 a piece. The chip it has a low voltage cutoff of around 2 volts. So I think if I drive it with something that can deliver current at 2 volts, then I should be able to get some higher voltage out of it. And the hope is to charge a 12-volt battery with that. So I'll probably need something like 14.5 volts or so. But this is supposed to be able to go up to 28 volts. All right, I just wanted to go over a few of the calculations I used to calculate what I needed for a generator on this small turbine. I've gone through this spreadsheet in a previous video, so I'm not going to go into too much detail. Just want to say I set up my load voltage as 3.6 volts, so I got about 1.2 to 1.4 volts for diodes and 2 volts for the low voltage cutoff, and just a little bit of headroom there. Then I chose a cut-in speed of 2.6 meters per second. It's 5.8 miles per hour, so it seems to be a reasonable value for the wind that we see. I've got a C sub P for the turbine of 0.12. It's a guess. I think it's reasonable, but it's just a guess. Tip speed ratio 0.62 under load. That again is just a guess. My turbine is 110 millimeters in diameter, 180 millimeters tall, and pretty much the main things here are I've got at 3.6 meters per second with this TSR that I've got. We're looking, I'm sorry, 2.6. We're looking at almost 280 RPM, and so we get a volts per RPM available. And then we've got the stator resistance, and that's something that we have to pick. So I've got a graph here. The yellow curve is the theoretical power available from the wind turbine. The blue curve is the theoretical power that the generator is consuming. And then the red curve here is the power being delivered to the load. So if I choose a stator resistance that's fairly low, say 40 ohms, then we see that the generator is consuming more power than the wind turbine can source. So it's a little bit too strong for the turbine. If I put something that's a little bit high, like 60 ohms, then we see that the generator is not consuming all the power that's available, so we're wasting some of it. So I found that 50.6 had a generator load curve that was similar to the wind curve. And if you look at the efficiency of actually power going to the load compared to the wind power, it peaks out at about 4 to 5 meters per second, which is good because that's where we often see wind when we actually have wind. Okay, then the as far as the generator design, we've got our specifications. volts per RPM and resistance. I've chosen just to use 12 millimeter magnets, 3 millimeters thick, and I'm just running with that, and no steel backing or anything like that. And using FEMM, I'm estimating an average magnetic field of 0.08 Tesla through the coil. So then the next thing is to actually do the design, to pick wire gauges and number of turns and number of poles and that sort of thing. So I've repeated, this is the volts per RPM I'm shooting for. This is our stator resistance that I'm shooting for. And I made a table with different number of poles. And with a certain number of poles, then I can figure out how many turns I can fit in there and at what area of wire to get to fit the resistance requirement and the space constraints that I've got. Okay, so but I don't have complete control over what kind of area of magnet wire I can get. So what I do is I find out approximately what kind of area I'd want, and then I take, using wire gauges tables, I can pick a wire gauge that would give me an area that's just the next lower than what I have, and then it recalculates the number of turns I can have to meet the resistance requirement. And then once I have the number of turns, number of poles, I can figure out what kind of magnetic field I need. And I know that I want 0.08. So it turns out if I have 10 poles, 32 gauge wire, 163 turns, I meet my resistance requirement, and I have enough magnetic field to hit the voltage requirement.
For 163 turns. So that's 163 turns. Okay, now I have to get this coil off, and I got this kind of scored part here, so I just flex it. Just flex it there, and if you bend it enough, the coil will come off. And if the form doesn't break, you can use it again. Oops, gotta be kind of careful of that wire. So there we go. There's the coil. I'll put some additional tape in between and then form it into the coil holder, which is here. So the tape will go in between each of these slots, and then I'll feed the wire through the middle here and stake it down with hot melt glue. And then I can take this cone and run some flat screws in. I've got number 4s that are 1/2 inch long, and those will attach the coil holder to the cone where the bearings will be and that sort of thing. Okay, I soldered the magnet wire to some lead wires and checked the resistance. I was showing about 51.3, and now I'll tuck this down and then apply some hot melt to hold it all in place. But that's the coil so far. Okay, here we have 10 poles. These are 12 millimeter diameter magnets, 3 millimeters thick, and they're just alternating polarity. I have a 100 millimeter long, 6 millimeter diameter shaft in here, and this is just a little spacer. This allows you to adjust the height between the magnets and the coil. And here's the coil. It's already been screwed to this cone. The cone has a 6 millimeter ball bearing and a 6 millimeter bronze bushing pushed way down inside. I don't know if you can see it in there. The bronze bushing is 10 millimeters in diameter and 10 millimeters long. And this is the collet that goes into the EMT tubing. So then this cone goes here, and the turbine just fits in there. And then the magnets just pass right over the coil. Alright, I've got the oscilloscope hooked up to the generator. I don't know if you can see that, but I'm just going to give this thing a spin and see what we get for a voltage. Just do a single sweep. And it looks like we've got peak-to-peak voltage of 6.56, and the frequency is 53.8 Hertz. So using that information, we can estimate how many volts per RPM we get, and we can compare that to the design. Alright, here's the peak-to-peak voltage data. I tried a few runs and recorded the frequency of the waveform, converted that to RPM, just using this expression here, and then calculated volts peak to peak per RPM. It's fairly consistent. Could take an average, got 0.0204. When I designed it, I looked at just the peak divided by RPM, so I just divided that by 2, and it was 0.0102. If we look at my design, I was looking for 0.01286 right here, so we're about 21% low on our voltage. Measured the coil resistance, 51.4 ohms. The design was 50.6 ohms. So we're about 1.5% high on our resistance. I think I can help that. There's a pretty good gap between the magnets and the coil, and I think the magnets ended up sitting a little bit deeper into the turbine than I thought when I mounted them. So I think I can take the spacer and just shrink it down, bring the magnets closer to the coil, and help this number, so I can boost the magnetic field and get this number up a little bit, or closer to the design. So I'll see how that goes. Okay, this is the original spacer. Excuse me, I replaced it with a thinner one so that the gap between the magnets and the coil was less. I retook the data and ended up with an average volts peak to peak per RPM of 0.0232, and then divide that by 2, get 0.0116, and the design was 0.0129, so now we're only 10% low instead of 21% low, so bringing the magnets in helped quite a bit. Still a little bit low, but not too bad. Okay, there's the turbine spinning in the wind. We've got this kind of red and white or black wire coming up in here, connected here to a rectifier I had earlier. It's a 3-phase, but I'm just using two connections there. Then after it gets rectified, it goes into this little boost board, and then from the boost board it goes into here. Has to pass through a couple diodes in there, but that's
I'll just live with that. And that feeds the battery right now. So there's no current showing, but I don't expect a whole lot from this thing anyway. And I have to adjust the voltage so that this voltage is high enough to charge the battery. So I got to work on that yet. But that's the circuit. I'm not 100% certain this is a good setup. I suspect that when this voltage gets high enough to overcome the battery voltage and the diodes, it starts conducting current, which immediately draws down the voltage here and sends this plummeting below the low voltage cutoff, and then it goes down again. So it's possible it might just kind of rise and fall with, you know, just kind of oscillate, or maybe it just won't function well at all. But it's an experiment. Okay, there's the turbine. It's feeding the rectifier here, which goes over to the boost circuit, and I'm monitoring the voltage across the boost, and that goes through the charge controller into the battery. Anyway, that's the waveform we're getting on the output of the boost circuit feeding the battery. But it's so light right now that it doesn't really show up as current, or it's just not, doesn't have quite that much power. So it's not really showing up on the current meter. But there must be a little bit of current going in. It's probably on the order of 1 or 2 milliamps, if anything. So I'd say that this setup might work, but I think it's very inefficient. We're only producing a few volts, and we lose probably a volt on the diodes, so there goes 30% of our efficiency. And then this thing is going to have some efficiency as a boost circuit, so that's probably only like 75–80% efficient. And so we're I think it'd be better just to wire the generator so it can feed this battery directly without this intermediate step here.